what is left now, differential forms, for now at least, is to do this residue theorem. Okay, so the theorem is this. It says that let X be a compact Riemann surface. Let I would say P1, Pn belonging to X endpoints, and let omega be a holomorphic one form on X. Take away these endpoints, right? A1, P1, P2, Pn. So we have a holomorphic one form, which is holomorphic everywhere except at this endpoint. Yeah. Then sums of residues of omega at pi is equal to 0. So you notice this is a kind of nice version of residue theorem, which is true on compact Riemann surfaces. Okay, so let's see how we can prove it. So proof is just a consequence of a Stokes theorem, or use a Stokes formula. Right. So this is your Riemann surface. It's compact, right? It has some genus, doesn't matter. And you have these points P1, say P2, and then you have Pn, right? So then what you do, you just choose n coordinate charts around each of them. 1, 2, and this is the nth one. So pick coordinate charts. Charts U1, U2, UN around P1, P2, Pn, such that, so under this coordinate charts, I want this UI be actually made biholomorphic to the open disk, such that UI actually goes biholomorphically to the open unit disk, say. The set of all Z in C, such that absolute value of Z is less than 1. Okay, so we just, I mean, yeah, we can do that, right? This is in C. Okay, now we are going to use the Stokes formula for this domain now. So if you use the Stokes formula, what does the Stokes formula says? Let's see. Let me just raise this. Okay. Okay. So use the Stokes formula. Yeah, so one thing you notice is that, okay, so this residue of omega, right? The residue of omega at pi, we just defined it. But if you bring this omega to this open unit disk, the residue can be calculated as an integral, right? So this is equal to integral over some
U sub I is isomorphic to the open unit disk.
What's that?
Each u sub I.
Yeah, H U by I, but then I'm going to write it as actually maybe I have to choose this a little bit smaller. So I just choose it such that this, okay. This is like analysis. You have to choose epsilon equal to epsilon over 3 from the beginning of the argument. Otherwise, if you don't choose epsilon equal to epsilon over 3, then you have to go back and change everything. So now I have to choose actually a line, circles, I mean, boundaries which are smaller. I don't want to be this boundary to be exactly here where that's not. So, now this is equal to integral of, so phi star of omega basically over this boundary of phi I of ui, which is really now integral of omega over this boundary of ui. You see, why that's the case? Originally, we defined residue. You see, our original definition of residue was this. Residue of some AI zi I from minus infinity to plus infinity turns out to be equal to at pi turns out to be equal to a minus 1. I mean, we defined it. That was our definition, right? But if you integrate this, because we are now in a coordinate chart, if you integrate this, this is equal to integral of f of z dz over boundary of, okay, phi I of ui. I mean, this is really the 1/4 phi star of omega. You see that? I mean, the point here. So because residue, you can define it using power series expansion of the function around the pole. And you can also define it as integral of this function, or 1/4 actually, at the circle around the pole, right? This is two definitions. We are using that fact. And that fact is very easy to establish because, I mean, this just follows from the following result. Integral of z over Zn over any disk, over any boundary of this disk. It doesn't matter. So basically, this is equal to 0 if n is equal to, okay, so I have to adjust that a little bit. If n is equal to different from 0, but different from -1, and is equal to.
And it's different from 1.
Sorry?
And it's different from 1.
N is different from 1, yes. And is equal to 2 pi I if n is equal to 1, yes. Okay, so this is then a minus 1, so it should be 2 pi I this. Because this integral itself is 1 over 2 pi I, but we are not interested in 2 pi I, we are just interested in the. Okay, now what we should do next? What we should do next?
The multiple.
Sorry?
The multiple.
Add them all, yeah, okay. If you add them all, then you have actually integral over boundaries of this thing. So let's add them, yeah. And you get that sums of residues, indeed, that's what we are interested in. Omega at pi, I from 1 to n is equal to 2 pi I integral over boundaries of these coordinate charts, which are here. These are the interior ones. Nice, of omega. Okay. Now, how do you calculate this line integral, this integral of this one form? Stokes. Third time, yeah. This was utter third time. Yeah, so how? This is equal to integral of d omega, right? I mean, so let me put it like this correctly. D omega over this, so let me write it correctly, over x minus union of ui, I from 1 to
Times 2 pi I, times 2 pi I.
Oh yeah, times 2 pi I, yes. Thank you, yes, exactly. Now, what is this? So we have to know what is d of omega. What is d of omega? Omega, what was omega? Omega was a holomorphic one form. Well, metamorphic one form, right?
Pose at n, but if we're taking it without the open sets containing the pose, the integral would just be 0.
Yeah, and we are away from these zeros. We are in the complement of these unions of these disks even around that. And that's 0. So d of omega is equal to 0 on this x minus union of ui, I from 1 to n. Because, I mean, this is the holomorphic one form. Remember what was the holomorphic? D, as I proved, is equal to del plus del bar of omega, and this is equal to 0. Holomorphic one forms are closed. We know that. I checked it. Okay, so this is the end of the proof. And this 2 pi I doesn't matter because 2 pi I times 0 is also 0. So that's good. So it shouldn't bother us. Exactly. Okay, so this is a very nice result because any questions? So that's very nice because now I mean, we will use it again and again, of course. This is like used many times. But one immediate corollary is the following. It's a result that we proved actually. And now I'm going to give another proof. So immediate corollary of residue theorem. So this was proposition. So this proposition I can say like this. Let f from x to c be a meromorphic or non-zero function. And x compact. So we have two conditions. We have a compact Riemann surface. We have a non-zero meromorphic function on x, right? So then what did we prove about this? Then what did we prove about this sort of situation? Remember, we proved it actually. Yeah. We proved that some orders of f at p for all p is equal to 0. That's what we proved. Right? So now I'm going to give another proof using the residue theorem. So note, proof, note. This is already proved, but we just give a second proof now, which is good. So how can we prove this, possibly? We are going to create a meromorphic one form using this meromorphic function, and then something like magic happens. So here is the proof. Consider the meromorphic bound form. Meromorphic one form. What meromorphic one form do you suggest to choose? Well, there's no way to know. It's df over f. I mean, I just say del f over f.
What's the difference?
Hmm?
Del F was-
In this case, there is no difference because f is meromorphic. Del bar is 0. So and d is equal to del plus del bar,
Okay.
and then so on. So I just write df actually. In fact, I need the fact that I'm glad you insisted on this. So which is del f as well. But this is a meromorphic bound form. You see that by this is a meromorphic bound form, right? It's clear because df is a bound form. You have a function, you differentiate, theorem differentiate, you have a bound form. And because f is meromorphic, which means holomorphic away from poles, it's a holomorphic one. And dividing by this is also is completely harmless because we want the only thing we need is just a meromorphic function. That's all. So now we are going to apply residue theorem to this, right? Okay, so apply residue theorem to omega. So what you get then, we get that the sums of residues of omega df over f at all p's over p is equal to 0. Right? Now something, as I said, something like magic happens is the following, that the residue of this guy is actually the order of the function at that point. No, so I mean a simple, check now, this is something you have to check. That residue of these logarithmic one forms actually are exactly the order of p of f. It could be minus order of p of f. I have to check what is order actually. Okay, so how would you check this? How would you check this statement? Because you see, you agree that if I check this, then we are done because the sums of residues is sums of orders of the function, and then you're done, right? So how do we check this? So you see that the only points that matter are zeros and poles. That's the only points that matter for this. We just have to study this around zeros and poles, right? So let me give you an example. So of how this calculation goes. E.g., let f of z be locally, because we are doing it's just completely calculus computation now. It's nothing but that. So locally, let's write f of z equal to say z minus z0 at some point to the power n. For example, n could be positive, negative, or 0, whatever. Right? Now, so what is the order of, so let's take n positive. What is the order of f? At p, or I mean, in this case, it's 0. That doesn't matter. It's p is equal to n, right? It's a 0 of order m, so order of f is 0, is m. So let's compute df. df is m times z minus z0 to the power m minus 1. Right? And df over f is m times z minus z0 to the power m minus 1 over z minus z0 to the power m. So now this is something, there's a cancellation, and this is equal to m over z minus z0. So this is a simple pole. No matter what you do, you always get a simple pole. This is equal to m over z minus z0. So obviously the residue is m. That's it. So this implies that the residue, at least of this one form, this simple function for this simple function, residue of df over f. In this case, at least, you can see that z0 is equal to m, which is order of f at z0. And this calculation goes through. If m is negative, same thing happens. If you just expand it, you just get this. The calculation is same. That's the essence of the idea. That also, but the message is very important. The residue of these logarithmic poles are always order of the original function. So this is a very deep fact, actually. It's not some gimmick. It's a very, very deep fact. Yeah. Okay. What else I have to do? Looks like I don't even have to do anything else. Then we go to divisors. Any question? Question? No? Everything is clear. Well, that's good, yeah. Okay. So now let's go. So we are going to. So this is part of the machinery we need later, very soon, actually. So now another thing is divisors. Okay, so divisors on Riemann surfaces, or divisors of Riemann surfaces, I don't know. Surfaces. So this theory can be done for non-compact Riemann surfaces, that's fine, but it's easier to do it first for compact case. So let X be compact Riemann surface. So a divisor on X is just a map D from X to the abelian group of integers Z such that D has finite support. Okay. D has finite support. So what does this mean? It means that D of X is 0 for almost all X except for finite number of points. So i.e. D of X is equal to 0 for all X except finitely many. Except finitely many. And there is a notation, there are variations on this notation people use. D is equal to sum dp P. This is just denoted like this. It means that the value that it attains at P is dP, but we have to keep that in order. So these are like basis.
What's uppercase P?
What's that?
What is uppercase?
What is what?
P times P. Oh,
it's not times. It's like so think of P here as a basis of a vector space or a module actually. I will tell you now what it is. Oh yeah, I'll tell you. Okay. So we just write. So it's clear that divisors form an abelian group. It's clear that divisors form an abelian group, a huge abelian group. You can add, because you have these two functions on X, you can add them in the domain, in the target space. You can add them, and there is a negative of an element there, and you just everything is there. There's 0, which is 0 divisor. D equal to 0 is a 0. Okay, so this is this is denoted by div x. Div x. Now, you can also think of this divisor, group of divisors in a different way. It's the same, but it's in a different way. This is the free abelian group generated by X. Okay? So this is alternatively also the same as free abelian group generated by X. I mean, it looks crazy because it has uncountably many generators, so all the element points of S. Yeah.
Sorry, what's the group operation?
Oh yeah, the group operation is addition. D1 plus D2. I mean, if I want to define as a function on X, the value at P is going to be equal to D1 of P plus D2 of P. And you see that if this has compact support, this has compact support, the sum is also have compact support because this is 0 away from finite number here, finite number, the union of two finite is finite and is 0 away from those. So that's really a finite abelian, that's really an abelian group, but it's a crazy abelian group because it's free, but it has uncountably many generators, right? It's just like something. You don't see these things in courses in algebra because it's just there is no use for that over there. Okay, so this is this one. Okay, so we have that. Then I define a degree function for these divisors. The degree of a divisor is degree of a divisor. So this is this function dig from div x to z. So degree of d is equal to sum of d of p, p belonging to x. And the kernel of this degree function is called obviously zero divisor, 0 degree divisor. So div 0 of x, this is called degree 0 divisor. Degree 0 divisors. Divisors. Okay. So we have this subgroup div 0x, which is a subgroup of div x. Now I define a subgroup of div 0, which is the following thing, so principal divisors. So let's define the principal divisors. So let f belonging to m of x be a meromorphic function. Then the divisor of f is equal to, so this is denoted by div f, little d of f is equal to some order of f at various points p times p. So we just look at the order of this meromorphic function at different points. So obviously p matters only on zeros and poles. Away from that, this is 0. The order of the function is 0, and then just divides. So then the set of all principal divisors are called. So such a thing is called a principal divisor. So let me define it, and then I'll just tell you what it is. So. So definition. A principal divisor is a divisor of the form div f for some f belonging to mx meromorphic function. For some meromorphic function. Now you can see that these principal divisors actually form an abelian group.
A divisor is defined from X to Z. How do you define a divisor per direction?
How do I define? Sorry?
Oh, I'm sorry, no, never mind.
It's the definition is here, yeah. The definition principal divisors are here. Okay, so what is going on now? I want to check, and that's not difficult, is that principal divisors actually form an abelian subgroup. So let P div X equal to a set of all principal divisors. Right? So we take the set of all principal divisors, and now this is a subgroup. I mean, this is a little lemma, is that P div X is a subgroup of div 0 of X. Proof? So the only thing that, there are two things that matters. First of all, we have to show that it's a subgroup of the thing. So there's a degree issue, we have to show that. But the other one is that why the sum of two principal divisors is a principal divisor. Right? So I've got div F, one principal divisor, you add another principal divisor. Why the sum is a principal divisor?
Multiply the two.
We can multiply the two, and this is going to be, this works. So this is, in fact, this is you check here, and this is okay, yeah. I mean, for example, if you have a pole of order, I don't know, this or that, you can just see that this poles are going to be. Now, the other thing is, for a principal divisor, we want to check that degree of principal divisor is 0. So why? Well, this is a theorem that we proved twice. The second time was the last lemma that I proved, right? So this is sum. In fact, this degree is equal to sum of order of P, F at P, right? Over P, which is 0. That's 0. Okay, so that's the end of the proof of this lemma. So the picture that emerges is the following very interesting picture. Now we have a sequence of groups. You should keep this in mind because it's always very important. So then we have got P div X is a subgroup of div 0 of X. And this is a subgroup of dx. Okay. So we have this picture of a sequence of groups. Now, from here to here is not a big issue. I mean, there is not a big difference from here. This two. Why? Because I can find a section for this map. So this sequence splits. Div 0 splits. So let me show you. I mean that's pretty easy, but it's kind of important to know. this injection of subgroup div 0x inside, so let me put it like this, inside div x. Oh, what am I trying to say? I mean, I'm trying to say that the difference between these two is not that much. Okay? Splitting is not the right word, maybe. Because that one is much bigger than, I mean, this one is bigger than that. So I define a map here, right? Let me tell you. So, okay, so let me tell you like this. It splits non-canonically. In other words, what I'm trying to say is the following. Let's define a function. Pick Q belonging to x. That's the non-canonical part you do. You pick a point on x, right? And define this S from div x to div 0 x. So we do it in the following way. Oh no, it's not good. That's not good. No, what I'm trying to say. No, this is splitting is not the right terminology. What I'm trying to say is that div x is isomorphic to div 0x. Div x sum z. So okay, so what about the following maps? So I just take this map div x to z. Okay, I want to finish. So we go to z. I mean, this is the degree map. Not degree. I mean, it's not degree. I mean, this go. Okay, so it's the following. Sends a divisor d to degree of d. Yes, degree of d times p. And this is a divisor. And now, what about this?
Professor, what is P over here?
Hmm?
What is P?
Oh, I picked the point P. My choice
Okay.
on X. Okay, let's see if it works. I mean, okay, so I don't want to spend too much time on this, but let me just try this. So then I want to define another map div x to div 0x. I mean, this is this should be, what's it called? It's called this. Actually, no. I mean, this is an augmented group. That's the point. Have you heard about augmented groups? No. Okay. So augmented groups are exactly that have this map into Z. So div x into div 0x. So the map is not like the following. D. I map it to, but that's not a group homomorphism, unfortunately.
Can you take like a map from dx to z? It will be your
What's that?
From divisor of x to z. It will be like your augmentation, and the kernel of this map will be 0 divisors. So you will have exact sequence, short exact sequence, and I guess that's exact sequence splits. And this give you like your statement then.
Yeah. I wanna show that actually this is true.
Yeah, so but that's just about the splitting of short exact sequence.
Yeah. So what is the short exact sequence?
So you take an augmentation map from divisors of
Yeah,
x.
this is the augmentation map. but I have. Wait. I mean, okay, so yeah. So this was, so no, okay, so I want to do it this way. I have this map, div x, which is degree. This is the augmentation map.
Yes.
And the kernel is, the kernel is div 0. And then I'm saying that there is an augmentation here. There's a splitting here. And this is the splitting map.
So that's a Schrodinger sequence?
Wait. So I'm just sorry. Let me finish. So this is the splitting map. So S of say n is equal to n times p. Yeah, this is something totally stupid, but it's should be true. But I mean, just I'm not very convenient about this now. So
I think that's correct, right? Compose that with the other one, you get the identity.
yeah, this is correct. This is a splitting, but there is something that bothers me still. Okay, so
Is it true for?
anyhow, this is a splitting. So no, that's correct. Let's. I mean, it doesn't play a big role in what I'm trying to say. I'm trying to say that the difference between this and that is just one Z, one abelian group Z. It's like really, this guy really has codimension 1 inside this space. So the difference between the two is not that big. But the difference between these two is quite interesting. And that's why we take the quotient, and that's called the divisor class group. So let me write it. So the divisor class group, I don't have a notation for it, like divisor class group is the quotient of div 0 of x divided by p div of x. And to understand the difference between this and that is the content of Abel's theorem. So Abel's theorem gives us necessary and sufficient condition, which I will prove gives us necessary and sufficient condition. For a degree 0 divisor to be principal. To be principal. So I will get it in maybe 3 weeks towards the end of the course, but this is quite an important theorem. Now, one thing I wanted to say is there is an analog of this group actually in number fields. Have you seen this? What's that? It's called ideal class. This is the exact analog of ideal class group, and that measures how far or how much unique factorization into primes fails in a number field, an algebraic number field. So there is a dictionary. So we are trying to build this dictionary between Riemann surface theory and number fields. And this is another thing. This is called ideal. Analog of this is called ideal class group, which is so you take fractional ideals and all that story, which is so this is a pretty important group. However, so let me finish by this. So here's an example. Again, in the case of x equal to p1, things are completely boring. Or x equal to p1, any divisor of degree 0 is actually principal. I can show that. That's not difficult. Any degree 0 divisor is principal. So, I mean, just write down any degree 0 divisor, and then you just construct this middle. I mean, so this is okay. So I just give it as an exercise. But this already fails for the torus. Already fails for the torus. So this is wrong for. It's not true that any degree zero divisor on elliptic curve is principal. There's a condition in terms of the size of, in terms of location of the lattice points. So wrong for genus of x bigger than or equal to 1. In all cases, this is wrong. So this is a good exercise with rational functions we work. So what is the analog of this in number theory then?
And now P1 and
Q. So you can say Q or Z, think of integers over in Q, which is Z, unique factorization holds, so ideal class group is trivial. Of course, there are many other number fields. Of course, ideal class group is trivial, but Q is Z. Okay, so I believe I don't want to say more because then I get into what I want to do.
I have a question.
Yes.
This is the Picard.
Picard group. Yeah, the name of this group.
Yeah, you call it divisor.
Divisor class group. Yeah,
This is the Picard.
this is the Picard group. Maybe divisor class group, I have to take all of it by this one. Yeah, Picard group because it's the connected component of this divisor class group. Yeah, because these are degree zero line bundles. Yeah, essentially. Yeah, there is a whole story of divisors in terms of line bundles. We'll visit that. So this is kind of line bundles. They are very geometric objects that appear themselves, show themselves in this kind of mundane language of 3 abelian groups and stuff like that. But then there's a much deeper geometric theory behind. And this degree, if you write your divisor as divisor line bundle, its degree is actually integral of the first chain class of the line bundle. So it's a very topological invariant. So yeah, so I think we can okay.